Welcome to today's episode, where we're diving into the fascinating world of distributed systems. These systems are woven into the fabric of our daily lives, powering everything from the phone calls we make to the online banking services we rely on. Yet, despite their prevalence, many of us might not fully grasp what they are or how they work. So, let's break down the key concepts, challenges, and algorithms that define distributed systems, helping you gain a clearer understanding of this essential technology. At the heart of a distributed system is a network of independent computers that come together to achieve a common goal. Each of these computers, often referred to as nodes, operates with its own local state and communicates with other nodes through messages sent over various communication links. This interconnectedness allows tasks to be shared across multiple machines, enhancing both efficiency and reliability. What's really interesting is that these systems are designed to keep functioning even when individual components fail. For example, if a remote computer goes down, it might affect your local machine without you even realizing it. This vulnerability highlights the necessity of creating robust systems that can handle failures gracefully. As technology evolves, we've come to recognize the limitations of traditional vertical scaling. This approach involves upgrading a single machine to boost its performance, but it can be both costly and complex. Instead, horizontal scaling has emerged as a more effective solution. This method is all about adding more machines to the network, allowing the system to grow and adapt without the hefty price tag of expensive upgrades. Take modern database systems, for instance. Gone are the days when they relied on a single node. Nowadays, they're typically designed as clusters of multiple nodes, which not only increases storage capacity, but also improves performance and availability. This distributed architecture enables organizations to handle larger volumes of data and user requests more efficiently. While the theoretical foundations of distributed computing have been around for quite some time, practical applications have surged in recent years. This growing interest has spurred increased research and development, leading to innovative solutions that tackle the complexities of distributed environments. As we navigate through distributed systems, it's essential to grasp some fundamental definitions. The participants, or processes, interact through message exchanges, and their local states can vary significantly. This variability adds complexity, especially since remote processes might communicate over unreliable links that can introduce delays or failures. One of the primary challenges in distributed systems is the inherent unreliability of communication channels. Messages can be delayed, reordered, or even lost, complicating the task of maintaining a consistent state across all nodes. Additionally, processes can encounter failures, such as crashing or becoming unresponsive, which can disrupt the overall functionality of the system. To address these challenges, researchers have focused on developing distributed algorithms. These algorithms are crafted to manage both local and remote states, ensuring that the system can continue to operate despite the uncertainties of the network. They define the roles of participants, the messages exchanged, and the transitions between different states of execution. Speaking of algorithms, they play a crucial role in the functioning of distributed systems. They outline how multiple independent nodes interact and coordinate their actions, which is essential for reaching consensus. So, what exactly is consensus? It's the process of achieving agreement among various processes on a specific value or state. Coordination is a fundamental aspect here, as it involves supervising the actions of multiple workers to ensure they collaborate effectively to complete tasks. This cooperation is vital for disseminating information quickly and reliably across the network. In essence, distributed algorithms help synchronize efforts among participants, allowing them to work together seamlessly. Now let's touch on some key concepts that will help deepen our understanding of distributed systems. First, We have participants, which are the individual nodes or processes that comprise the system. Each participant has its own local state and communicates with others to achieve shared objectives. Then there are communication links, through which participants exchange messages. The reliability and speed of these links can vary, making it crucial to consider their characteristics when designing effective distributed systems. Another important concept is state and transitions, where distributed algorithms describe the local behavior of participants and the transitions between different states. Each process executes algorithm steps locally, and the combination of these local executions and interactions forms the overall algorithm. Achieving consensus among multiple processes is a significant challenge in distributed systems and requires careful coordination and communication to ensure that all participants agree on a specific value or decision. Lastly, we must consider failure models. Distributed systems need to account for various failure scenarios, including message loss, process crashes, and network issues. Designing algorithms capable of handling these failures is critical for maintaining system reliability. As we delve deeper into the practical applications of distributed systems, we'll explore various communication patterns and their implications. We start with User Datagram Protocol, or UDP, which allows for message sending without any guarantees of delivery. This approach is particularly useful in scenarios where speed is prioritized over reliability. As we progress, we'll examine more complex communication patterns that require higher levels of assurance, ultimately leading us to consensus algorithms. These algorithms are essential in situations where multiple processes must agree on a value, such as in blockchain technology or distributed databases. In conclusion, distributed systems are a vital component of modern technology, facilitating seamless communication and collaboration across vast networks. By understanding the fundamental concepts, challenges, and algorithms that define these systems, we can better appreciate their significance in our daily lives. With the growing interest in distributed computing, we can expect further advancements that will enhance the efficiency and reliability of these systems. Thank you for joining us today as we explored the intricate world of distributed systems. We hope this episode has provided you with valuable insights and a deeper understanding of how these systems operate. Stay tuned for our next episode, where we'll dive into more exciting topics in technology and innovation.